Thanks the organizers to give me the opportunity to speak. Today I talk about a new point of view for intrinsically Lipschitz graph in the Franchi-Serapioni and Serra-Cassano sense in metric spaces. This is joint work with Enrico Ledonne. In the first part of my talk, I recall the notion of rectifiability set. Then I present the intrinsically Lipschitz map in the Franchi-Serapioni and Serra-Cassano sense. Then I give the notion of intrinsically Lipschitz section in metric spaces. And finally, I give properties and application of this notion. So the question is, why do we study intrinsically Lipschitz maps? The answer is in order to establish a good notion of rectifiability in particular metric spaces called Carnot groups. As we know, E, a subset of Rn, is decountable rectifiable if it is possible to cover it with a countable union of the graph of Lipschitz maps Fi from Rd to Rn minus d. Ambrosio and Kirchen proved that this definition does not work in Carnot groups. One possible solution is given by Franchi-Serapioni and Serra-Cassano, and in the context of Carnot groups, they introduce the intrinsically Lipschitz maps. Which is the idea? They define suitable intrinsic cones, which are not equivalent with Euclidean cones, but the idea is similar. And they say that a map 5 is intrinsically Lipschitz if for all points belongs to the intrinsic graph, there exists an intrinsic cone such that the intersection between the intrinsic cone and the intrinsic graph it's just the point P, the vertex. In the picture, it is possible to see the model case H1, which is R3, with not commutative operation group. And in the red part, there is an example of intrinsic cone. In the blue part, there is an example of intrinsically Lipschitz map. As I say, this is a research with Enrico Ledonne. We generalize this notion in metric spaces. In Franchi-Serapioni and Serra-Cassano approach, they consider intrinsically Lipschitz map. In our approach, we consider graphs. This is really important in order to extend this notion in metric spaces. Obviously, metric spaces are more general than Carnot groups. In this context, the proofs are short and simple, and we use basic mathematical tools. So, now I present our definition. We have X metric spaces, so you have a set and you have a distance. Y is a topological space, so you have a set and you have a topology. And pi is a map from X to Y, is a quotient map, meaning continuous, open, and surjective. We say that phi from topological space to metric space is an intrinsically Lipschitz section of pi if it is a section, that means the inequality 1 holds, the composition between pi and phi is equal to identity of y, and finally we want that the inequality 2 holds. So it is possible to compare 2 points, phi y1 and phi y2, with the distance between phi y1 and the fiber of y2. What meaning the inequality 2? Meaning that, as I said, it is possible to compare 2 points with a point and a fiber. In the picture, we know that if we consider the projection, pi is the projection, the fiber of y2 consists in 2 points, these 2 points, this and this. The intersection between the red line and the X. Basic facts. Because 5 is a section, then 5 is injective. Because of the inequality 2, L is larger or equal than 1, and we study the inequality 3 holds. That meaning we study a sort of by Lipschitz condition. Behind intrinsically Lipschitz is equivalent as behind a by Lipschitz embedding when pi is a symmetry. That meaning that it is possible to in the pi of the ball centered in x, point of x, is equal to the ball centered of pi x. Now I try to explain what is intrinsic cons. Given x, point of x, and L larger than 1 or equal, we define the set CXL as the set of all point x prime belong to x such that the inequality 2 is not true. In this context, it is easy to see that we consider pi a quotient map and phi a section. Phi is L intrinsically Lipschitz if and only if phi y intersecting this set is empty set. In the Franchi-Serapion and Serra-Cassano approach, instead of phi y, we have the graph of phi. In this sense, we consider the graph of phi. More precisely, if X is a Carnot group, CXL is exactly the intrinsic cone in the Franchi-Serapion and Serra-Cassano sense. Now I present an easy example. We consider X the union of A1, A2, and A3, a subset of R2 with Euclidean distance. A1 is the set of all points x4, x between 0 and 1 included. A2 is the set of all elements x0, where x is a number between 0 and 1 included. And A3 is the set of all elements 1x, with x is a number between 0 and 4. We consider Y an interval 0, 1. We don't say what distance we suppose in Y because, as we say, the Y is just a topological space. We consider pi from x to y, the projection map on the first component. So pi of A1 is equal to x, pi of A2 is equal to x, and pi of A3 is equal to 1. In this context, H fiber pi minus y consists in 2 points. For instance, this is a y. The 2 point is this and this. Just in one case, when we consider the fiber of 1, we have all of interval A3. In this context, we consider f from y to A1 defined as fy is equal to y4, and g is from y to A2 defined as gy is equal to y0. In this context, f and g are both intrinsically one Lipschitz section of pi. Together with Enrico Ledone, we prove the following properties of the intrinsically Lipschitz section: the continuity, with additional hypothesis, suitable hypothesis, the Ascoli-Herzela theorem, Alfors-David regularity. We prove a link between intrinsically Lipschitz section and the level set of by Lipschitz map, the extension theorem, a Leibniz type formula. We get an equivalent relation and we get a vector space over R. We conclude, given an easy proof of this research, we prove the Alfors-David regularity. I recall the set. We have X a metric space, Y a topological space, pi is a quotient map, and phi is an intrinsically Lipschitz section of pi. We recall the definition Alford-David regularity. Let Q a number larger to 0. Phi y is locally Alford-David regularity, Q regularity, with respect to the measure mu, meaning that for each point x belong to phi y, there exists R0 and C larger than 0, such that it is possible to compare the measure of the ball centered of x with R power q. Okay. Which is the additional hypothesis that now we want. We want that there exists a measure mu on y such that for every R0 larger than 0 and every point xx prime belongs to the same fiber, there exists a constant c such that the measure of the pi of the ball centered of x is larger, not larger of c of the measure of the pi of the ball centered of x prime. Which is our thesis? If phi y is locally Alford-David Q regular with respect to the push forward of 5 mu, then for any other intrinsically Lipschitz section psi from y to x, the set psi y is also locally Alford-David Q regular with respect to the measure given by the push forward of psi mu. An easy proof, as I said, I recall the hypothesis. Let phi psi intrinsically a Lipschitz section with L is larger or equal than 1. Fix a point y belong to y. We know that phi y is Alford-David regularity, that meaning that inequality 4 holds. We want to prove that the same inequality, but now we consider the map psi, holds too. Which is the three properties that we use to obtain our thesis. We consider that phi y and psi y belongs to the same fiber, and so we have these equalities. It is possible to compare the measure of pi of the ball centered of psi y with the measure of pi of the ball centered to phi y. The second property follows by the definition of push forward, and the third properties follows by easy computation. Using these three properties, it is possible to prove that the push forward of psi mu of the ball centered in psi y is larger or equal than a suitable constant, depend on L, C, and C1, of R power Q. Using the same properties, it is possible to prove the other inequality. Putting together these two inequalities, we have that the push forward of psi mu of the ball centered of psi y, it is possible to compare this number with R power Q. Thank you for the attention.